Uh, assume a change at the source of sound reduce the wavelength of a sound wave in air by a factor of 2. What happened to its speed? Assume a change at the source of sound reduce the wavelength of a sound wave in air by a factor of 2. What happened to its speed? Okay. We have the formula for the relation between the speed, the wavelength, and the frequency of the sound of the wave in general as V equal to F lambda. Okay. Now, the question assumes that the source of the sound reduces the wavelength by a factor of 2. It means that lambda change to half of lambda. What happened to its speed? To answer this question, you need to know that when you change the wavelength of the wave from the same source, from the same generator, what will happen to the frequency? Because you can see that V is equal to F lambda. So if we change lambda, but we have to know also what happened to the frequency before we can calculate the velocity. So if you change the wavelength, what will happen to the frequency? Assume that we use the same generator. Somehow we change the wavelength of the sound. For example, if we change the medium, like first we generate the sound wave in the oxygen environment, and then we change to the nitrogen. So we change the medium, or we change the density. Or we change the environment allow the source of the sound. So we can change the wavelength. What will happen to the frequency? Lady in pink, before you go to have a sweet dream, what is the change in the frequency? If you use the same source, if you use the same generator, what is the change of the frequency? ไม่ change. Nothing. Do you agree? How do you know that it's correct? Yes, that is the correct answer. There is no change in the frequency if you use the same generator, because to generate the wave, the sound wave, okay, the generator will have to vibrate to make the change or to disturb. Yes, we use the word disturb, to disturb the medium. Okay, and if you use the same generator, it means that you disturb the medium with the same frequency. Okay? But the response of the medium can change if you change the environment. Like if you change the type of the gas surround the generator, or if you change the temperature, you change the environment around the generator. So we can change the wavelength. We can change the wavelength here. So if the frequency does not change, if you reduce the wavelength by the factor of 2, what will happen to the frequency? Okay? Now you can answer this question. If you reduce the wavelength by a factor of 2, what is the change of the speed? What is the change of the speed of the sound? In this case, F does not change. The frequency does not change. So, if you reduce this by a factor of 2, what is the change of the speed? Okay? So this is for the question number 1. For the question number 2, the intensity of a sound wave at a fixed distance from a speaker vibrating at 1 kHz is 0.6 watt per square meter. This means the intensity that results if the frequency is increased to 2.5 kHz while the constant displacement amplitude is maintained. Okay. In this question, it gives the intensity of the sound equal to 0.600 watt per square meter with the frequency of 1 kHz. With the frequency of the 1 kHz. Now, they say that if we change the frequency change to 2.5 kHz, while the amplitude, the displacement amplitude is maintained. It means that you have the same amplitude of the wave of the sound, but you change the frequency. What is the change of the intensity? Okay? Change from 0.6 to what? To answer this question, you have to know the relation between the intensity, the frequency, and the amplitude of the sound. Okay? We have the formula. The intensity is equal to the half of the rho is the density of the air. Okay, the velocity of the sound wave. Omega is the angular frequency, and A is the amplitude of the sound wave. And this is omega A square. Okay? Now, they say that if we change, okay, if we change the frequency of the sound wave by while maintain the amplitude of the sound wave, what is the intensity after we change the frequency? Okay, so you can see that in this equation they give the initial intensity here, and they give the frequency. From the frequency you can calculate the angular frequency. Okay, and they say that at this value of frequency we have this value of intensity. And now if you change the frequency to from 1 kilohertz to 2.5 kilohertz while you maintain the amplitude, what is the final value of the intensity? You may ask that when you change the frequency, what happened to the density and the velocity of the sound? The density of here is the density of the air. So how do you think that does the density change with the frequency? It is the density of the surroundings of the air surrounding the generator. So should it depend on the frequency of the generator? Okay. The velocity of the sound. We have the formula for the velocity of the sound as the square root of B over rho. Okay. Rho is the density, while B is the bulk modulus of the air. Okay, the bulk modulus of the air is the parameter that describe the elasticity of the medium. In this case, it's the air. Okay, it's like the Young modulus. When you work with the when you work with the elasticity of the string, okay, we use the Young modulus to determine the elasticity of the string, but that is the object that has the shape of the string. The bulk modulus has the same property, but it describes the elasticity of the object in the bulk. I mean, it is the response of the pressure when we have the pressure on an object and an object change its shape, which means it's changed in 3 dimensions. The volume of the object change, and the bulk modulus describes the elasticity when we look at the change of the 3-dimensional object. Okay? So, this is the property of the medium. The bulk modulus is the property of the medium. So, do you think this property will change with the frequency of the generator? It's a property of the medium. Okay? So, if you put a generator, do you think it changes the bulk modulus of the medium? So if you can answer that should low and we change with the generator or not, you can answer this question. Okay, so that is for the question number 2. Now let's go to the question number 3. Suppose you hear a clap of thunder 16.2 seconds after seeing the associated lightning strike. The speed of light in air is is about 3 times 10 to the 8 meter per second, and the air temperature is 20 degrees Celsius. How far are you from the lightning strike? Okay. In this question, there is a lightning. Okay, you see the lightning. Somewhere. You see the lightning. And after you see the lightning, you hear the sound of the thunder 16.2 seconds. It means that you have the lightning and it produces the thunder. Okay? And the sound of the thunder travels to you. Okay? The sound of the thunder travel to you. Before, when there is a lightning, it means the light travel to you also, right? Now, if you are at the distance S from the source of the lightning, you are at a distance x from the source of the lightning, and the light travel with the speed c. C is the speed of light, and the thunder, the sound of the thunder, move with the speed of v. Okay, move with the speed of v. So you can see that the time that the light travel to you the time that the light travel to you is equal to the x over c, right? If c is the speed of light, x is the distance from the source of the thunder or from the source of the lightning to you. So the time that light travel to you is x over c. And the time that the sound travel to you is x over v. And in this question, it gives you the TL minus TL minus TS is equal to what? 16.2 seconds. Okay, 16.2 seconds. So it means that you have that x 1 over c minus 1 over v is equal to 16.2 seconds. Okay. So from this equation, you can calculate the value of x, the distance from the source of the lightning to you. What left that you need to know is the velocity of sound. Okay, it's the velocity of sound. We have that the velocity of sound is equal to 331 times the square root of 1 plus TC over 273. Okay? Here, TC is the temperature of the surrounding, temperature of the air. Temperature of the air in degrees Celsius. Okay? It's the temperature of the air in degrees Celsius. This is the TC. So, they give you, in this equation, they give you TC is equal to 20 degrees Celsius. So you know everything. So from this, you can calculate X. Because you know C, you know the value of the I think I write something wrong here. It should be TS minus TC, right? Because the time that the sound travel to you is longer than the time that the light travel to you. Okay? So this should be V and this C. Okay? Switch the position of V and C. Okay? So that is for the question number 3. For the question number 4, a point source emits sound wave with an average power output of 80 watts. Find the intensity of the wave at the distance 6 meters from the source. Okay. The point of this question is that the source is a point source. Okay. The source of the sound is a point source. It means that the source is very small and it generates the wave in all directions out of the source. It means that it generates the wave out of the source in all directions. Okay? This is the meaning of the point source. This is the meaning of the point source. And we know that the power output of the source is 80 watts. So it means that at the point source, here it generates the power of 80 watts. Okay? It generates the power of the 80 watts. And this power is transmitted to the air. Transmit to the air. So, it means that if you look at on the area or the spherical area that have the source at the center, if you look on an spherical area that has a source as the center, and if you measure or collect the energy of the sound wave from on the area of this spherical surface, you will get 80 watt of energy, 80 watt of the rate of the energy transfer. Okay, you always get the 80 watt of the rate of the energy transfer on the surface of on the spherical surface that has the source as the center. Okay, but here is asked the intensity. Is asked the intensity of the sound. So what is the definition of the intensity? What is the definition of the intensity? The intensity is the power divided by what? The intensity is the power divided by the area. Okay, the power divided by the area. This means that if you look at this spherical area, the area of this sphere, the spherical area here, and if you divide it by the power, which I told you that is equal to 80 watt, and you divide it by the area of this sphere, you will get the intensity. Okay? So, in this case, what is the formula for the spherical surface? The area of the spherical surface. What is the formula of the area of the spherical surface? It's 4 pi r squared. It's the area of the spherical surface. Okay? So, they say that if you look at the point 6 meter from the source, it means that from the source, if you look at this point, 6 meter away from the source. So it means that we have R is equal to 6 meter. So you know R, you know A, and you also know the power. This is the power, sorry, not the work. This is the power. Okay? You know the power, you know the area. So, can you calculate the intensity? So this is very simple. Okay? Next, okay. The question number 5, a sound wave moves down a cylinder. The displacement of the medium is, from that equation, the pressure variation of the wave is described by which one? By the equation, the following equation. Which one? A, B, C, or none of above. Okay? In this question, you have to understand that when we talk about the sound wave when you talk about a sound wave, you can describe the sound wave in two ways. You can describe it as the a displacement wave, and you can also describe it as the pressure wave. You can describe it as a displacement wave, but you can also describe it as a pressure wave. What does it mean? When you generate the sound wave, okay, for example, if you have a speaker, and the diaphragm of the speaker vibrate, okay, to generate the sound wave, you compress the air. The air try to, when you compress the air deform, okay, and it try to go back to the equilibrium position. So it means that when you generate the sound wave, you will have the region of the air that the air move because from the compression, okay? You will have that we have the area that the air compress, something like this. So we have that in this region the air is compressed, something like this, okay? So when we look at the displacement of the air, where should we have the largest displacement? You can see that around this region we must have the S max here, but around this region we have S equal to 0. Why? Because when you disturb the air moves forward, right? For example, here, if the speaker disturbs the air moves forward. So it compresses the air beyond the speaker. So it means that the speaker pushes the air around here to compress the air beyond the speaker. So the air here moves. Okay? So we have that this is a region that the air moves. And it compresses the air beyond. So we have the region that the air is compressed. Here, when the air is compressed, so it means that there's some part of the air that's not moved and some part that move. If all the air moves, there is no compression, right? If the air moves to the left and the air here the air here moves to the left and the air here also moves to the left, there is no compression, right? So it means that there must be the region that the air does not move and the air from the speaker moves to compress the air. So we have that this is a region that the air moves a lot. Okay, this region and this region. And where the air is compressed, it means that the air doesn't move. Okay. So, this is the way we describe the wave as the displacement wave. This is the way that we describe the wave as the displacement wave. Now, if we look at the pressure, you can see that here, where the air is compressed, what should be the value of the pressure of the air here? Is it larger or smaller than the atmospheric pressure when the air is compressed? The pressure should go higher or larger than the normal pressure. Okay? So, we must have that we have the maximum change of the pressure here. You can see that we use the word delta P. We use the word delta P because we cannot have the region that the pressure is equal to 0 in the air, right? If the pressure is equal to 0, it means that it is in the vacuum. It's in the vacuum. So, this is the change of the pressure from the normal atmospheric pressure. When the wave, the sound wave pass to the air, the pressure can change from the normal atmospheric pressure to some pressure. Okay, and here is the maximum compression here. So we have the change of the pressure is maximum. And when there is the maximum displacement, the density of the air here should be lower than the normal value. Okay, the density of the air here should be lower than the normal value. So when we have less dense air, what is the value of the pressure? We have the less dense air. We should have allowed here delta P min, delta P minimum. Okay? So, if you compare the displacement and the pressure, you can see that at the maximum pressure, you have the displacement equal to 0. At the minimum pressure, you have the displacement maximum. Okay? So, if you look at the wave as a sinusoidal wave, what is the phase difference between the sound wave and the pressure wave? What is the phase difference between the displacement wave and the pressure wave? If we assume that the pressure wave and the displacement wave, the pressure wave and the displacement wave is a sinusoidal wave, so what is the phase difference? What is the phase difference of these two waves? What is the phase difference? If you write down the sound wave, you have the maximum displacement allowed here. You have the 0 displacement allowed here. You have the maximum displacement allowed here, and you have 0 displacement allowed here again. So you have the maximum displacement and you have the zero displacement, and you have the maximum displacement, and you have zero displacement again. Okay? And if you okay? So, this is a sinusoidal wave that describes the displacement wave. Now, if you write down the pressure wave, you have the maximum pressure here. You have the maximum pressure here. You have the minimum pressure here. And then you have the maximum pressure again. And then you have the minimum pressure again. So, what is the phase difference between the displacement wave and the pressure wave? What is the phase difference? The phase difference, you can see that the phase difference is pi over 2, right? The phase difference is pi over 2. So, if you have two sinusoidal waves with the phase difference of pi over 2, if one wave is represented by the cosine function, what should be the other wave represented? You have that here they say that the displacement wave is represented by the cosine function, right? S max cos kx minus omega t. So, if the red line is a cosine function, and we know that the orange line has a phase difference of pi over 2. So, what should be the function, the functional form of this orange line? It should be the sine, right? Because we have the phase difference of the pi over 2. So, now you need to know a little about the mathematical trick. What is the value of sine square theta plus cos square theta? What is the value of sine square theta plus cos square theta? 1. Okay? Is equal to 1. So, we can write down that the cos theta is equal to 1 minus sine square theta, and take the square root, right? Okay, sorry. Oh, okay, we can also write this that sine theta is equal to 1 minus cos square theta okay, we have to use this relation, and we also know that delta P max is equal to rho V omega S max square. Delta P max is equal to rho V omega times S max square. Okay? From this information, can you write down the relation between delta P and S? Is it follow the choice A, B, or C? Okay? I give you this information. And you know this information, the relation between the pressure wave and the displacement wave. Can you answer the question number 5? What should be the relation between delta P and the displacement S? Okay. Now, go to the question number 6. Increasing the intensity of a sound by a factor of 100 cause the sound level to increase by what amount? First, you need to know the definition of the sound level. What is the sound level? The sound level, okay? By the definition, the sound level is equal to okay? This is the definition of the sound level. The sound level is the 10 times log of I over I0. This is the definition of the sound level. Okay? If you look at this equation, you can see that the sound level has no unit. The sound level has no unit because it's a ratio of the intensity. I0 is the minimum value of the intensity that the human can hear. Okay? Okay, I0 is the minimum intensity that the human can hear, the minimum intensity of sound that a human can hear on average. Okay, so normally the sound level has no unit, but we will give the unit to this quantity to let us know that we talk about a sound level. It's something like we give the unit to the angle at the radian. From definition, the angle radian has the angle has no unit, but because it is the ratio of two quantities with the same dimension, the length, the arc length, and the radius. Okay. Anyway, we will give the unit to the sound level as a decibel. The decibel. Do you have any idea why they use the word deci here? Why they use the word deci here? They use the word decibel, but what is the meaning of the word deci here? What is the double L should be what is the meaning of deci here? Deci mean 10 times by 10 or the step of 10. We know that centi is 1 over 100, right? Centimeter, it means that you know that 1 meter is 100 centimeter. But 1 meter is, we have 10 decimeter in 1 meter. So it's a factor of 10. And it comes from this factor, 10. Okay? We times 10 to the log of I over I0. Okay? So we call it the decibel. Now, if you increase the intensity by factor of 100, what should be, what is the increasing of the intensity? Oh, sorry. What is the increasing of the sound level if you increase the intensity by the factor of 100? Okay. When you increase, for example, here you increase I to 100I. If you increase the intensity from I to 100I, what should be the value? What should be the increase of the sound level? What is the change of the sound level? Okay? It change by 100 decibel, 20 decibel, or 10 decibel, or 2 decibel. Okay? Use this relation to answer. Next, question number 7. A source of sound wave is moving toward an observer. Which of the following statement is true according to the observer? It means that you have a source of the sound wave, and the source of the sound wave move toward an observer. You have an observer here. A. The wave speed is highest in front of the source. The wave speed is highest in front of the source. Okay. B. The wavelength is largest in front of the source. C. The frequency is highest in front of the source. And D. All above are correct. Okay, all above are correct. The point of this question is that the observer is still relative to the medium. So it means that like we stand still in the air. So if there is no wind, if there is no movement of the medium, it means that the air is at rest relative to the observer, and the source moves toward to the observer. For the choice A, the wave speed is highest in front of the source. Does the wave speed depend on the motion of the source? Okay, we have that the speed of the sound wave V is equal to the square root of B over rho. Okay? It is anything related to the motion of the source. Okay? This is for the choice A. B. The wavelength is largest in front of the source. Is it true? You can see that when the source generates the wave, when the source generates the wave, it also moves toward to the observer. So it means that when it generates the first wave, the wave moves to the observer, but the source also moves to the observer also. So the time it generates the second wave, the distance between the first and the second wave, if you compare the distance between the first and the second wave, in the case that the source moves toward the observer and the source stays still, what should be the distance between the first and the second wave? Is longer or is shorter in front of the source, in front of the source? Okay? And if we look behind the source, if we look behind the source, if you have the source, it creates the sound wave, and the source moves away from the wave, and it generates the second wave. So, what should be the distance between the first and the second wave compared to the case when the source is at rest? Should we have the larger or the smaller wavelength behind the source? Okay? So the choice B say that the wavelength is largest. The wavelength is largest here. Is that correct? Okay, that is for the choice B. The frequency is highest in front of the source. What is the frequency? What is the frequency? When you hear the sound, it means that when the source generates the first wave and it moves to your ear, and then the source generates the second wave and it moves to your ear, the number of the wave that hit your ear in 1 unit time is the frequency, right? So if the source stays still, it generates the first wave to you, and then it generates the second wave to you. The time between the first and the second wave is the period, and the inverse of the period is the frequency. Okay? Now, the source generates the first wave, okay, and the wave moves to you, and in the same time the source moves and generates the second wave. So, how do you think that the period of the wave that you hear will increase or decrease? The period of the wave that you hear will increase or decrease? It generates the first wave, the wave go to you, the source move, it generates the second wave go to you. Should the period increase or decrease? Okay? If you think that the period increase, so we should have the smaller frequency. If you think that the period decrease, you should have the larger frequency. Okay? So, that is for the number C, the choice C. Okay? Next. Your clock radio awakens you with a steady and irritating sound of frequency of 500 Hertz. One morning, it malfunctioned and cannot be turned off. In frustrating, you drop the clock radio out of your fourth-story dorm window, 15 meters from the ground. Assume the speed of sound is 343 meters per second. As you listen to the falling clock radio, what frequency do you hear just before you hear it strike the ground? This is about the Doppler effect. This is about it, the Doppler effect. In this problem, they say that you are at the fourth-story dorm, which is at 15 meters high from the ground. Okay, so this is 15 meters high from the ground, and you drop a radio clock. You drop a radio clock from the distance 15 meters to the ground. And during the clock drop to the ground, it generates the sound to awaken you. First thing, do you think that the frequency of the sound will increase or decrease when you drop the clock? When you drop the clock, do you think that the frequency will increase or decrease? In fact, if you can answer this question, you can choose the right answer immediately. When you drop the clock, okay? For example, while the clock is here, it will generate the sound wave. So, as similar to this question, when I ask you that when the source moves, behind the source, I mean here, like here, what should be the wavelength of the sound compared to the situation when the source is at rest? Does the wavelength longer or does the wavelength shorter when the source moves in this direction and in this region? The wavelength is longer or the wavelength is shorter. Okay? And when you look at the formula of the velocity of the sound, you can see that the velocity has to do nothing with the motion of the source. The velocity has to do nothing with the motion of the source. So, if you say that here lambda is longer, you must have that frequency is smaller. But if you think that lambda is shorter, we must have that frequency is larger. Which one you will choose? Longer or shorter? Okay? As I told you, if you choose the correct answer, red or green, you can give the answer to the question number 8 immediately. Okay? But if you have to calculate the value of the frequency, You need to know the formula for the Doppler effect. Okay, for the Doppler effect in this case. I will give you the formula later. Okay, but here, can you answer? The wavelength is longer or the wavelength is shorter? If you can answer this question, you can answer the question number 8 immediately. Okay? Now, let's go to the question number 9. A submarine A travels to the water at a speed of 8 meters per second, emitting a sonar wave at a frequency of 1500 Hz. The speed of sound in the water is 1533 meters per second. The second submarine B is located such that both submarines are traveling directly towards each other. The second submarine is moving at the speed of 9 meters per second. While the submarines are approaching each other, some of the sound from sub A reflect from sub B and return to sub A. If this sound were to be detected by an observer on A, what is the frequency? What is its frequency? Okay? This is a little bit complicated. We have submarine A move with the speed of 8 meters per second, and we have the submarine B move with the speed of 9 meters per second. First, the submarine A generates the sonar wave of the frequency of 1500 Hz. Okay? One thousand and 500 Hz with the velocity that is the velocity of the sound is equal to 1533 meters per second. Okay? This sound wave hit the submarine B and reflect back to A. Okay? This sound wave hit the submarine B and reflect back to A. Okay? They ask that if you measure the frequency that reflect back to B from B, I call it FA prime. Okay? What should be the value of FA prime? Okay? This is a little bit complicated because there is 2 steps to calculate this. You have A generate the sound with the frequency FA, this 1500 Hz. This value of 1500 Hz is the frequency of the generator that a person on A will hear the sound. It is a frequency relative to the person on A. This is a 1500 Hz. Now, if you are a person on B, when you hear the sound from A, will you hear the sound with a higher or smaller frequency? The sub A moves to B, right? And it generates the sound of the 1,500 kilohertz, 1,500 hertz to B. That 1,500 hertz is related to the person on A. And if you are a person on B, what is the sound that you hear? Frequency. What is the frequency? Okay, you should hear the frequency that is higher, right? You should hear the frequency that is higher. So, B will hear a higher frequency. And when the sound hit B, it will reflect back. So it means that it will reflect back with the same frequency as B here, right? It will return the sound with the same frequency. Okay? Now, for the second step, it means that B generate the sound wave. Okay? B generate the sound wave. And the person on A will hear that sound wave. Again, do you think that the person on A will hear the reflected wave from B with a higher or lower frequency? You should have the higher frequency, right? So, in the second step, the frequency FA prime, which is the frequency that the person on A hear the reflected wave, will be higher than the frequency that the person on B hear, right? So you have to calculate two steps. That you have to calculate the frequency that B hear from A, and then B generate the same wave. B generate the reflected wave with the same frequency, and A again hear the reflected wave with the frequency that higher than that generated from B. Okay? As I told you, I will give you the formula for the Doppler effect later. But before you do that, you have to understand the whole picture first. What should be the change of the frequency in this case? Okay? Now for the last one. An airplane flying with a constant velocity moves from a cold air mass into a warm air mass. Does the Mach number increase, decrease, stay the same, or unpredictable? Okay? First, you have to know what is the Mach number. By definition, the Mach number is the ratio of Vs over V. Okay? The Mach number is the ratio of the Vs over V. Okay? Vs is the velocity of the source. To understand this, have you ever seen why you have the jet plane move with a very fast, with a high speed? It will generate the large sound. Okay? At that time, we may have that the jet plane move with a speed that higher than the speed of the sound. Okay? So it will generate the shock wave. In that, to determine that whether the jet plane generates the shock wave or not, we can do that by looking at the Mach number. The Mach number is the ratio of the velocity of the, for example, of the jet plane, which is the source of the sound, over the velocity of the sound. V is the velocity of the sound. Okay? Now, in this case, they say that if you have the jet plane fly in the cold air or in the warm air, should we have the change on the Mach number? Should we have the change on the Mach number? Assume that the jet plane moves with the same speed. So, Vs does not change. The point is that what is the change of V when we change the temperature? When we change the temperature. Okay? When we change the temperature. I give you the velocity of sound, right? The formula for the velocity of sound. This formula. Okay, we have the formula for the velocity of sound like this. So, if you change from the cold air to the warm air, what should be the change of the velocity of sound and what should be the change of the Mach number? Okay, this is quite simple question. Okay, so that is for all of the question for today. I will give you the formula for the Doppler effect, and now it's your time to do the detailed calculation.